Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and today it's just me on the live stream. I'm sometimes joined by an Oxford student, but I don't have one here today. That means it's just us together talking about some maths that I've got. I think everything's plugged in properly and everything's working. Hi to people in the chat. I've just been chatting to people before we go live. Hi to Amelia and Raf and Ali on screen. Hi to the username Darishley, and I saw Ali and Alfie here as well. I've got a plan for today to talk about some inequalities and parameters. Talking to the people before we went live, I've realised that more than any previous episode, I don't know what to call this one. I don't know what the title should be. So we're going to try and work that out during this live stream. Maybe that's a really bad sign. Maybe that's really bad. When it's been just me on the live stream before, things have sometimes got a bit weird or gone off the rails a little bit. We're going to see if that happens again today. Hi to other people. Hi to C and Harriet and Abigail. If you're joining us live, if you're watching live out there, then hi, it's great to have you with us. Hi Ali. You can join in the live chat at slido.com/OOMC. If you do that, then you can put things in there. And we have got, I think Hussein is in chat moderating. Thank you for moderating. Brilliant. Hi to Claudia as well. Things can appear on the screen without me clicking on anything. Brilliant stuff. Okay. I think live has started. Somebody in chat says, is live started? We'll find out. I'm just going to keep talking and see what happens. That's a terrifying message. Right, okay. Coming up today, we've got pie, more of it. I liked the pie last week, so I've packed even more pie into this week's episode. We've got donuts, if we get that far, and also pasta, if we get that far. We're going to try and get through all of those things. Maybe there's a theme there. I'm just so hungry. Right, okay, so that's the plan. This is the point in the live stream where I usually say you can get further reading on the Maths Club website, link at the bottom. Further reading is suspended during March. We're migrating a website over, don't ask. But further reading will follow at some point in April. That's also the page for all the past episodes and all of the other stuff like that. It feels weird not having anybody else on. It's been a while. Hi, Zach. Hi. So people in chat, is live started? No, people think it's not started. Say Alfie and Ali. That is suspicious. Pretty bad news. Let me have a quick look. Am I live streaming on the right one? Ha ha ha. I've got no viewers. No, I don't know what's going on. Ooh, this is very scary. People are saying hi. It has started now. Okay. It started. Okay. It started. We're live. This is happening. YouTube's giving me some very, very strange messages. Okay, I'm going to keep talking and assume that at least somebody's looking at this. It's working now. I can hear you. There we go. Okay, right, cool. Cool. I'm just going to carry on. Let's go. I want to talk about inequalities. I want to talk about what it means to solve an inequality. We might have something like, in school, you might learn to solve something like this. So if I give you this as an inequality, you learn how to solve that. I put solve in quote marks, like the bunny ears at the top. I put solve in quote marks. We'll talk about that in a moment. Just as a warm-up chat, partly so I can tell if you can see what I'm writing. Can people solve this inequality for me in chat? What would that mean for you? Oh, somebody's going on unique maths. Oh, brill. Yeah. Oh, and other people in chat are doing unique as well. Unique's going to be great fun. There are going to be about 3 different weeks, I think, for mathematics. So we're going to do the same residential program 3 times. Cool. So this is where I sit here like a lemon and see if anybody can see what I'm writing and solve my inequality for me. Ah, good times. The joys of being live. Oh, look, Alfie's here. Okay, cool. Thanks, Alfie. And YouTube started giving me data, so that's nice. Thank you, YouTube. Zach's here too, and there's anonymous. Or different expressions as well coming in. I think Harriet's here, people are rearranging this expression and then doing something to get it down to, look, I like this one, minus square root 3 less than x. I realise now that I gave you one where it involves square roots, which are hard to type into the chat. Thank you for doing your best. Hi, Molly. Something like this. So I quite like this because it's got a nice range of values of x. So this gives us some range. Oh, look at that, Molly's got a keyboard that does square roots. And we've got promise as well. Cool, okay. So I think this was called solving the inequality when I was in school. It feels a little bit like solving simultaneous equations, right? You start with some equations, some expressions, and then you try and rearrange them to get x equals and y equals. That's the rule for solving simultaneous equations. Where here, solve an inequality seems to mean get it into some form with x between some limits. So people think these things should not be included. Oh yeah, so sorry, being precise on inequalities, which caught me out last week. Question about unique, since we've mentioned it. I don't know how that's being run. Let's not read too much into it. Sometimes these programs send out emails quite slowly to different people. Let's not assume anything. Yeah, okay, so this is something I learned to do at school. Seems like people in chat have learned to do this as well, to rearrange things to get them down into some sort of range of values that satisfy. It feels neat, right? Like the original equation is not that complicated, but this final answer feels pretty good. We've got this rule about values of x. So I'd like to try and take this to higher dimensions to talk about inequalities with more than one variable in. And when we do that, it's going to be not clear what the answer should be. So we're going to try and remember this. That wasn't this nice that we started with an inequality and we ended up with x between some limits. Okay. Maybe we could try and do something a bit like that for other things. Not complex numbers yet. Okay, right. So higher dimensions. Here's the question as I phrased it. I've done my best to word this question. I'd like to know which points, in terms of x and y, are inside a circle of radius 1 with centre 0, 0. I'm going to draw that circle, even though I know that you know what that circle is. There you go. It's one of those ones where my picture can only make things more confusing, especially if I draw it badly. Yeah, okay, so I would like to know which points x, y are inside that circle. I suppose maybe this should say the circle of radius 1. Yeah, let's fix this question a little bit. Writing questions is hard. Some people have got inequalities coming in, so I like this. Abby's here, Alfie and Zach, Harriet. So the chat is a little bit behind the live stream, and it could be more or less behind the live stream, depending on how fast YouTube is sending you data for the live stream if you're watching live. Okay. So there's some x and y's going on. And then there's some z in here as well, so someone's quite keen to get onto the complex numbers already. I think z is normally x plus iy, right? Okay, some magnitude stuff, which I like as well. And I think I saw something. Yeah, so this is what we're going to work towards. Somebody's put separate ranges for x and y, which I love. It's not quite correct, but I know what you're trying to do, and we're going to try and work on that. Can everyone see this? There's this. Somebody anonymous has put x between -1 and 1, y between -1 and 1, which is necessary but not quite sufficient to be inside the circle. But we're going to work out why. Okay, let's write down this inequality that people are writing down in chat. This seems to be a popular thing to write down in chat. X squared plus y squared less than 1. Somebody's taken the username Andrew Wiles. X squared plus y squared less than 1. Okay, to me, this feels a little bit like the first line we wrote down for the previous problem. It's nice, it works, it's an inequality. It tells me about which points are inside the circle quite precisely. But maybe I would like to write this, kind of aspirational thing, is maybe I would like to write this as some range of values for x, if that makes sense. And maybe some range of values for y as well. To think about what's the range of values going on here? So somebody in chat wanted to write -1, x between -1 and 1, and then y also between -1 and 1. I like what they're thinking about. But if I put -1, -1, and 1, 1 on both of these, I think that gives me everything inside the square up to this point. I keep coming back to this anonymous person in chat, not because I'm trying to make a big deal about how they're wrong, because they're doing the thing that I'm interested in, which is trying to write some inequalities like this one. Cool. Yeah, that sounds like Andrew Wiles. Okay. So people have just later remembered the episode about metrics. So there's some sort of metric thing with IMI that we did a few weeks ago. So if you define some sort of new distance, maybe this is nice. And the people talking about R, I will get around to talking about R as well. Does this make any sense? I think, to know what I should write here and here, and also here and here, so that I've got some sort of limits on X and some limits on Y. They can depend, I suppose. Maybe I'll help you out. Maybe these ones could be numbers for the first one, and then okay, here we go. Maybe there could be some numbers, or maybe they could be functions of other variables. Now we can run into trouble like this, but I'm interested in that sort of thing. Okay. This is a very tricky problem to set. Maybe I could help by explaining why I want this. So quite often when you're writing computer code or something, you want to write a little for loop, and the for loop says start at this point and then change X through these through the values until you get to this stop point. And reading from start point to a stop point is something computers are quite good at with for loops. I'm thinking about maybe writing some for loops, and I only want to look at points inside the circle. Okay. Yeah, so people are starting to get to thinking about rearranging this expression, which I really like, to do something like this. So I think this comes from rearranging, just like we rearranged the other one, to rearrange this. I really like this. So this gives me some rules about, I knew what you meant, Harriet. This gives me some rules about which X values are inside the circle. This rule, which I really like, tells me that X goes between some value of Y and some other value in terms of Y. Implicitly in these expressions that Alfie's given me as well, implicitly I think I probably want to take -1 less than Y less than 1, because if I make Y too big, then these things will be horrible complex numbers, square roots of negative things. That I think that's not what Harriet and Raf and Alfie mean in chat. They don't want to do complex numbers yet. So chat's very keen on complex numbers, but I feel like they're not appropriate right now with these inequalities. So this is something interesting to me, because it says, okay, there's some range of values of Y. Y is between -1 and 1. And then for any particular value of Y, here's the range of values for X. X goes between something over here, minus square root of 1 minus Y squared, and over here, positive square root of 1 minus Y squared. Yes, cool. Yeah. There's this alternative, which is really the point I'm getting towards, I suppose. And I'm glad someone's put it in chat now. Who's this? It's Abika Khan has put in chat that, or we can write down something else. We can write down this to rearrange for Y, and to also, maybe I'll put with here to explain that these inequalities kind of go together. We could do it kind of the other way around. There's nice symmetry between X and Y. Could I say that X is real? Well, so I suppose I know what you mean. The danger is that I'd be saying that X lies between two complex numbers and is real, which, I mean, there's nothing that satisfies that, but also just doesn't quite work as an equation. Implicitly, you should limit the range of values of Y so that you don't take the square root of anything negative. Okay, we've got these alternatives because we could explain where points are inside the circle, by saying, well, first fix x between -1 and 1, and then if you fix the value of x, you can go between minus square root of 1 minus x squared up to positive square root of 1 minus x squared. That's pretty good. Okay, I will now indulge all of the people who've been telling me about mod z and people who've been telling him about r. Here's your version of this picture. So, people who like polar coordinates, here's your moment to shine. Could you give me, some of you have already said this, but could you say it again, please? For polar coordinates, where are the points inside the circle? Yeah, root 1 minus x squared looks a bit like sine squared plus cos squared, doesn't it? Yeah, there's something sine and cos going on here. That's, I suppose, the point of using polar coordinates, that polar coordinates are defined by x is equal to r cos theta, and y is equal to r sine theta. Yeah, okay. I like this. People saying r is less than 1, mod r less than 1, and any value of theta. Yeah, cool. Aha! Somebody's factorised into complex numbers. We're so keen on complex numbers. I shouldn't have admitted that there might be complex numbers coming in later. Yeah, people are really keen on saying that the points inside this circle are in r less than 1. Personal preference, I would also say that r should be a positive number. So r equals minus 37, I think doesn't really represent a point inside the circle. Secretly behind the scenes, maybe I'm interested in describing each point inside the circle exactly once. Or maybe I want this one to be an equals to, less than or equals to. Oh, hello, yes, cool. And I want any value of theta, and I'm going to be slightly more strict. Yeah, so theta can take any value, people are saying. Theta's a little bit weird. Theta is angle above the x-axis. So probably to get each point inside the circle once, I'm going to choose to take theta only up to 360 degrees, or 2 pi radians, I suppose. So kind of any value of theta, but any sensible value of theta. Somebody said, what are polar coordinates? Here are polar coordinates. It's a way to write points in the xy plane in terms of r, their distance from the origin, and theta, the angle above the x-axis. So any point in the plane you can write like this, using x equals r cos theta, some trig there, and y equals r sine theta. Okay, cool. If you haven't seen polar coordinates before, it's another way of describing where stuff is. And, ooh, wow, the thing I'm going to say in 20 minutes is going to be very confusing indeed. But don't worry, just come along for the ride. It's going to be fun. Okay, so we've got these alternatives for describing the points inside the circle. We've got this one. These are quite explicit ways of writing out which points are inside the circle, because they say here's y in some range and then x goes inside these ranges. This sort of equation where the variables are there, but it's not specifying a particular range. I might call this some sort of implicit equation, where it implies some points which are inside the circle and not. But it's not obvious when you look at it what the ranges are. Okay, so we've got stuff like this, we've got stuff like this, and we've got stuff like this to say, aha, here's a different way of describing what's inside the circle. Oh, it's easy in polar coordinates. That's the main selling point of polar coordinates. The stuff inside the circle is really straightforward. It's r should be between 0 and 1, and theta should be between 0 and 360 degrees. They're just numbers over on that side. So I'm on a year 13 lesson, and we're doing polar coordinates. Here are polar coordinates. It's just a way of saying where stuff is. And it's really good at saying where stuff is if the stuff is inside a circle. Cool. I've got a visualizer for this. I wonder if it's the right moment to switch to that. Maybe not. I think I want to show you some more examples first. I've got one that I should maybe have done first. Who's applying for Oxford next year? Yeah, I've got some more. So here's one I should maybe have done first, which is the square. Squares are easier than circles, so maybe this one should have come up first. So this is my square. It's got opposite corners at 0, 0 and 1, 1. I will draw the square for you. Maybe that's a bit of a weird way of describing a square. It's got opposite corners at 0, 0 and 1, 1. The other corners are 0, 1 and 1, 0, but I couldn't be bothered to write that out in the title. Here's the square. This one's a bit easier to describe where the points are. Inside this square. Maybe this was a better one to do first. But I like that we've talked about circles. We've done some rearranging to get those explicit ranges for x and y. Or, if you change the polar coordinates and you use those instead, explicit ranges for r and theta to describe a circle. Yeah, people are in for this one. Here we go. Even Andrew Wiles has had a go at describing this square for me. This is I'm gonna put my neck out and say that this is easier to describe. People are doing this extremely quickly. I'm going to go for strictly inside, and in general I think I'm not going to worry too much about the difference between strictly inside the circle or whatever and inside including the boundaries. And try not to worry about boundaries. Oh, there's a comma in that one. Nice one. Cool, okay. I think this is easier, right? So describing which points are inside the boundaries, there's only really one very sensible way, I think, to get away with this one, which is to do something like this. Maybe less than or equal to if you want to talk about the edges of the square as well. This means that this means that it's quite easy to integrate over squares. If you've got a square and you want to do some integration over all of the square, then it's sort of quite easy because you do your x integration, you do your y integration, you can sort of do them separately. The limits don't depend on the other variable. There's something about this in the double integration episode we did a few weeks ago, to think about those limits in terms of x or in terms of y. Aha! Just down arrow pointing at other people's suggestions. Cool, right. So squares. So here's a take. Maybe squares are easy with x and y, and circles are easy with these new polar coordinates that you learn in A level. I want to try and make squares seem a little bit more mysterious. Here's another one. So this is a square, but now I've put the corners at 0, 1 and 0, minus 1. I would like to know which points are inside this square. I've done these in the wrong order. I should have done the squares first, right? And then showing you the circle. Well done for joining in with the circle anyway. Okay. So I'd like to know which points are inside this. This one's a bit harder, I think, to describe. Let's try and find these corners. So this is 1, 0, minus 1, 0. This is 0, 1, 0, minus 1. Okay, cool. Ooh, some people in chat. People in chat seem to be more excited about mod signs than I was expecting. So there's some stuff about mod signs going on. Mod of x plus y. What does x plus y mean? So x plus y means if you're on the line y equals minus x, x plus y would be 0. That'll be this bit. And more x plus y less than 1. Okay, so that would be, I think, an entire region where x is very close to minus y, a million comma minus 1.5 million or something. Yeah, so people are very keen on mod signs. So I think some of the things people have put in chat are good and some of them are not so good, and there's room for somebody to come by and say something that's more simple and easier to understand than all the things with mod signs. So sometimes a healthy way to think about these regions, especially if you've got a lot of mod signs going on and you're working out, is to maybe think about separate regions. Yeah, so think about each of the 4 quadrants, says Ali. Here's some inequalities, okay, and this one's y in terms of, yeah, I like that, okay, I'm going to take that one, because I like the ambition from Erika here, to explain that x should be somewhere between, it says y is between x minus 1. So here's a suggestion, and I like it because we're aiming to get y as some sort of expression like this. So I think y bigger than x minus 1 would be bigger than this line over here, and y less than x plus 1 will be this line over here. So that sort of works as one equation, but I think it includes stuff over here as well. And Abby's given us, I think, the other one. Is that the other one? 1 minus x. Yeah. Okay. I'm going to go with... Oh, here comes some more inequalities. It's become collaborative. Yeah, so we think about bits and pieces, bit by bit, if we like. Maybe we could have some expression like this as well. We could try and piece things together. My first attempt when I saw this problem was to think about first limiting where x is, the kind of idea about, well, x doesn't take any value, right? X is between -1 and 1. And then y is between something that's some sort of function of x. And I need to work out what that function is along here. So when I first saw this problem, I turned it into a kind of name that function question for, aha, I can see that x, the points inside the square lie between -1 and 1, and then there's some name that function game for where are these points. Yeah, you can't just bring the L1 metric in. People learning about polar coordinates in this live stream. Time and a place, right? So Anonymous there has given me 4 inequalities. Do I like all of them? I think I like all of them. They say that x plus y. Ooh. Y less than 1 minus x, y bigger than y less than, right, let's try and write these down. Y less than 1 minus x, y less than x plus 1, y bigger than x minus 1, y less bigger than minus x minus 1. I think that works. I think that's the last one is this edge of the square, and then this one is y bigger than x minus 1. I think that's this edge, and then these top two are y less than x plus 1. That's this one, and y less than 1 minus x, that's this one. So you've got it on the correct side of all 4 edges of the square. I like that. So 4 inequalities, off you go. Cool. Okay, so some sort of list of inequalities we could do. I like that one because there's no mod signs involved. With my approach, I think maybe I want to try and work out this function, which I think might be something like 1 minus mod x or something mad. 1 minus the absolute value of x. Did I say y less bigger than minus x minus 1? Yeah, cool. That's me. Okay. So somehow, I guess the point of doing this one is that even squares are a little bit tricky in Cartesian coordinates if I rotate the square. Let's put out something interesting that someone said in chat, which I think was that this is between 1 and minus 1. I think some of the mod expressions mean this pair of inequalities. Have I got that right? I think these 4 inequalities are line up with the edges inequalities that someone gave me. I think this works. 1 plus y. I've got 1 minus x. I've got minus 1 minus x. I've got minus 1 minus x. Yeah, that work? Maybe that works. Okay. Assuming I've written that down properly, there's some pair of inequalities like this that's very interesting to me. So people with mod signs, I think you might have been writing down stuff a bit like this, using mod signs to say that the thing in the middle there is less than modulus is less than 1. Maybe that's what you already told me. I like this pair because there's just numbers on the outside. It feels a little bit like the punchline for the polar coordinates thing, where the polar coordinates expression had some limits that were just numbers on r and theta. But here I've got some limits that are just numbers for x plus y and x minus y. So if I did some sort of cheeky change of variables, or if I invented some new variables. Polar coordinates, some people just learned about polar coordinates for the first time. Maybe it looks like I invented them. I'm now actually going to try and invent something that is sort of newish. Can't call this new, what am I saying? If I write down u for x plus y, and I write down v for x minus y, that's sort of just as valid as the stuff involving polar coordinates. The polar coordinates gave me some new variables. They're called r and theta, which have some meanings to do with radius and angle, but I can invent new variables as well. I can call them u and v as x plus y and x minus 1. Then my inequalities are lovely. They say that I want u to be between minus 1 and 1, and v to be between minus 1 and 1. It's really simple, like the previous square. So somehow, if you choose the right variables, then you can write down regions in a nice simple way. Now obviously there's a little bit of a cheat there, right? That I had to choose some variables, write down introduce some new letters. But once I'd done that, I got a nice tidy answer. And there's something to this. I really should show you the circles next. Now I'm going to show you the circle. If you've come up with the idea of polar coordinates, r and theta, then as a result you get a nice expression for writing down where the circle is. And if you think of these u and v variables for this one, then you get some nice expression for where this diamond is. So that's pretty good. Sometimes thinking of the right variables can be the right way into a problem. Okay, I want to explore what you can do with polar coordinates a little bit more. That means switching over to a thing I've built in Desmos. We're going to do a very quick break while I switch over to Desmos and I check that everything's still plugged in and switched on and stuff like that. Somebody wanted a poll. I don't think I'm going to set up the poll live, but hey, the question was, are you applying to Oxford? If you're applying to Oxford, then hey, you might be interested in some open days we've got coming up. We've got open days for people who are thinking of applying this year for entry next year. And you can find those if you do something like search the internet for Oxford Mathematics Open Days. They're in April, and they're actually in person in Oxford, so you can come visit us. There's an actual advert. Oh, here's Nikita Mazepin. This is, for people who are new to the stream, this is a recurring character in the live stream. He's got the same name as an ex-Formula 1 driver. Okay, cool. Something matrix transformations. That's the sort of thing that I might put into the further reading if I was doing further reading in March. Okay, right, cool. We're doing okay? I think we're doing okay. Stream so far, bit ambitious, bit weird. It's going to get weirder, I'm sorry. I've got a Desmos thing I'm really keen to show people. Here we go. So this is my Desmos board. It's got a lot going on. Try not to look too hard at the stuff over here. What I've got is I've got some region over here where I can move the corners around to describe some rectangle. There are some sliders over here that are also moving. Try not to get distracted by the horrendous things I've done to Desmos to get it to do this. So I could use the sliders to move this rectangle around, but I prefer to grab the corners and move it around like that. So what I've set this up to do is, this is sort of, this lets me move the corners of the rectangle around to describe some rectangle. And at the moment it's just describing a rectangle, which we're really good at. We did that square lined up with the axes before. We're really good at describing what's inside a rectangle. But what I can do is I can tell Desmos to treat these as the two variables in polar coordinates. Okay, right, so, which is a very complicated thing. Here's how it's going to work. The thing across the axis, or across the horizontal axis, here is going to represent r, the radius, that variable, which if you met it for the first time is something like the distance from the origin. So that's going to be representing that. Now it's not equal to that, right? Because it's a rectangle, the points in it are different distances. But just imagining this being different values of r for these different, I guess, vertical blue lines that represent different values of r. And up the vertical axis, it's going to be different values of theta. So I'm thinking about different, the red horizontal lines correspond to different values of theta. So this grid represents a little bit of, I guess you could call it r theta space, for a little bit of what's going on in terms of r and theta. Okay, maybe that's a really confusing concept or really simple, I'm not sure. This is representing some range of values, r between 1 and a bit and 4 and a bit, and theta has some range of values here as well. Theta between 0.8 and almost 4. My point of showing you this rectangle is that it's kind of simple. R's got some range and theta's got some range. Now, represented in radians, yes, thank you, Drishley. Here's what I can do. I can tell Desmos that these are supposed to be polar coordinates. At the moment it's just showing me r as some range and theta as some range because it doesn't know what they are. I can tell Desmos to start treating these as polar coordinates. So if I do, then it's going to interpret that this range of r is going to mean a range of radiuses, and the range of theta is going to be a range of thetas. But maybe I'll stop talking and I'll show you what that looks like. So I need to switch this on. Oh, I switched this on and this on. Okay, there we go. Okay, right, here we are. Okay, so I've still got my control points, but they're not super important. So look, here's what I've got now. It's still sort of a grid, but it's smeared out. I've got some range of r, some range of radiuses, and I've got some range of theta angles. This is really good because this lets me describe different regions. We've already used this to describe circles, like this. Come on. Circles like this. So here I've set this to show me angles all the way up to 360 degrees or 2 pi radians. And I've set this one to say I want radiuses all the way from 0 out to 4 or 5 or whatever. But I can control that outer, what's the maximum r that I would like. And I can also control the minimum r, like this, to describe what's going on the inside. Say I'd like some range of values between r is 2 and r is 6 with a range of theta from 0 up to 2 pi. This region is called an annulus. Somebody in chat's beaten me to it. It's called an annulus, where it's sort of like one circle minus another circle on the inside. And let's take a moment to think about how difficult this would be to describe using x and y coordinates. So using x and y coordinates, we'd have to do something like, we'd have to say, well, x lies between -6 and 6, and then y lies between, depending on the value of x, maybe y lies between the bottom circle and the top bit of the circle, or maybe the bottom bit and the top bit of the circle. But when you get up to -2, no, y actually lies in these two bits of region. There's a bit up here and there's a bit down here, and then after 2, y lies in some range between down here and up here. This would be really tricky. Yeah, Nikita's reminded us that x is equal to r cos theta, y is equal to r sine theta in there. Yes, but in terms of, okay, so in terms of an implicit thing like this, a less than x squared plus y squared plus b, that's fine, that's true. That's because a squared plus y squared is equal to r squared, and that equation is much more simple if you write it in terms of r, the polar coordinate thing. Okay, so I guess I'm saying that this equation someone's just put in chat with x squared plus y squared in, it's a little bit complicated because it's got both variables x and y. If you can find a way to reduce that to one variable, then your life's much easier. You're describing these points in this annulus, or donut shape, in terms of a range of theta values and a range of r values. We do other stuff as well. So the power of this is I can change these and change what the limits are, so I can describe kind of rainbow shapes. They're not too bad at all. So this would be a pain using x and y variables. I'd have to maybe also say y is positive as an extra condition, or I would say, the range of x values depends on what your value of y is, and it's complicated, whether you take out the middle bit or not. And I can describe things that look like this, so I can do a range of sort of sectors or fans like that to say here there's some range of r values from 0 out to some value, and there's a range of theta values like this. Okay. Or even things like that. So I'm going to make a big letter C. I'm having fun. Cool. So complex numbers, complex numbers, complex numbers. Yeah, so complex numbers come into this because you can imagine r cos theta and r sine theta being the real and imaginary parts of the complex expression r e to the I theta. Let me write that out on this board over here. So there's this thing you learn at some point, which I think is called de Moivre. No, this is not de Moivre. Good times. Let's just write the maths out and attribute it later. Which is that you can write something like this for two different ways to write complex numbers. There's this way to write complex numbers as x plus iy, but there's this alternative form r e to the I theta. What does it mean to do exponential of a complex number? I don't know, maybe it means this. Where I suppose what we're really saying is that this exponential is sort of defined as r cos theta plus I r sine theta, which is sort of a mess, but does line up exactly with what polar coordinates are. So it's sort of a mess, but it's a related mess. So complex numbers. Yes, this then ties up because the fact people have maybe seen that if you believe in this, if you accept in your heart that r e to the I theta should be equal to x plus iy, if you accept that fact for some reason, then you have this lovely fact that as a result, that if I put in pi in radians, then I get r cos pi plus I r sine pi. In radians, pi does the same thing as 180 degrees. Cos of 180 degrees is -1. R in this expression is 1. So I end up with -1, and sine of 180 degrees is 0. So you kind of get this nice result as a result of just believing in your heart that e to the I theta, exponentials with complex numbers in, should behave like this. Then you get for free that e to the I pi should therefore be -1, which looks totally mad. People sometimes put great stock in writing it like this, so that it's got a 1 and a 0 in it. Some people really like that expression. Good, cool. It's quite handy having exponentials. It sort of says if you believe this, then exponentials and complex exponentials and cos and sine are sort of all the same thing. Anyway, I'm not sure I really wanted to show you circles though. The thing I'm really interested in for some maths that I had to do one time is ellipses instead. Do people know about ellipses? Let me tell you about ellipses really quickly. I can feel this turning into one of those live streams that's just a roller coaster mess of me saying way too many different things. So kind of want to show about ellipses. Ellipses work like this. So ellipses look a bit like this, where a and b can be different numbers. So it's like the equation for a circle, but stretched out by some scale factors in different directions. They go through, I suppose, a 0 minus a 0 0 b 0 minus b. I guess squishy circles, stretchy circles. Yeah, thank you. Good. Okay. So ellipses, I had a problem that I needed to solve, which had, rather than having a bunch of circles in it, which would be good for polar coordinates, had a bunch of ellipses in it, like this. So ellipses look a bit like this, different ellipses. If you've got different ellipses in your problem, then things are quite nasty to work with. You've got these x and y, some inequalities for describing what's inside that ellipse. You can write down an implicit thing to have x squared plus y squared. X squared over a squared plus y squared over b squared is less than 1. That would be some sort of equation for what's inside the ellipse. Implicitly, with x and y both in there. We can be a little bit hard inventing something that does that neatly for a nice pair of variables. So there are different coordinates, different ways you can modify this. One is to take this idea, x equals r cos theta y equals r sine theta, and to just stretch your coordinates. That is an option that's available to you. If you do that, then you get something like this. Maybe I stretch it this way. This is quite good now, because now I've got ellipses, which is what I wanted, and they go down to 0 like this, and they come out. I can describe different ellipses like this. These coordinates are quite good as a way of describing where things are, just polar coordinates that you learn about in A-level, but stretched. These ones are quite good if you want to solve problems where all of your ellipses are sort of similar to each other. They will have the same aspect ratio. And it's good if all of your ellipses share the same centre, like how the circles share the same centre. It's good if the ellipses share the same circle. But it's not perfect for all applications. My problems actually involved ellipses with different aspect ratios. I wanted something a bit like this, but with different ellipses on the inside and the outside, which sounds like a super specific thing to want, but that is what I wanted. That's sort of the way these go down to a point at the middle is okay, but it's not the only option you've got. It's also a little bit awkward that these coordinates, this is not a big problem, but these coordinates don't meet each other at right angles. They have all of these weird angles going on for how the red lines cross the blue lines. So that's a little bit weird. There's a solution which I found out about that is totally mad, and if you've met polar coordinates for the first time half an hour ago, then I'm really sorry for what's about to happen, but I want to show you a completely different set of coordinates that describes points in a different way. The modification's not that complicated, really. It says, instead of r cos theta and r sine theta, no. That treats r and theta quite differently from each other. What you can do instead is, instead of r, to use cosh of r with an h, so cosh, the hyperbolic cosine, and on your other coordinate to use shine with an h as a hyperbolic sine, to use these hyperbolic functions, which I think you learn about in further maths if you do further maths A-level or equivalent. So cosh and shine in there, with this weird choice of variables, with a cosh and a shine in, you can describe, again, ellipses, but the ellipses are quite different now. The ellipses now, instead of all going down to one point at the centre, they come in like this. I don't know if people can see this. They come in to share the same focal points, which is a property that ellipses have. They have these things called focal points. I'm going to put more ellipses in so it's more obvious what I mean. If I whack this up to, sorry, it's quite bad to look at, isn't it? If I whack this up to like 100, yeah, that seems good. Okay. So now maybe it's easier to see these blue ellipses. They all loop around the same 2 points at -1 and 1. Maybe if I open this up a little bit, you can see that these ellipses all shoot around -1 and they shoot around 1 over here. Even if I close this up, they're still going around those points. So this is good if you're trying to describe something outside that ellipse. Maybe you're trying to do some fluid dynamics problem with a pebble that's this shape and you want to work out the flow around that pebble. Maybe this is the wing of an aircraft or something like that. And it's quite good if you're trying to describe ellipses that are different squashedness, different eccentricity. It's also good because these coordinates are at right angles to each other. Let's bring this all the way down, okay. Are at right angles to each other. The red lines are at right angles to the blue lines wherever they meet each other. So this is quite fun. There's one technical point which I really like, which is going to make just absolutely no sense, but nobody can stop me saying it anyway, which is a subtlety to do with this shape. So this is describing everything inside a particular ellipse, in the y bigger than 0 bit of the world. With the stretched coordinates, this would be something like theta from 0 to 180 degrees, or pi radians. And these lines coming up from the origin would be theta equals 0, and on the other side theta equals 180 degrees. With these weird ellipsoidal coordinates, this is really subtle. I'm going to zoom right in. The bit on the x-axis is blue up to 1, and then it's red after 1. I don't know if that shows up on the stream at all. These coordinates are weird because the bit between, on the other side, let's have a look over the other side. Can people see this? It's kind of blue out to here, and then something swaps, and now it's red on the outside. So it's one of the red lines describes the bit from 1 outwards, and from -1 outwards, and it's a blue line that describes the bit between -1 and 1. Those are sort of different edges of the region. This is good if you're trying to describe something that's different between -1 and 1, different between -1 and 1 compared to what's going on outside -1 and 1. If I bring this down a little bit, and this up a little bit, yeah, okay, we can do something like this, where there's a little gap around here, but between -1 and 1, this comes all the way down to 0. So it's good if you've got something big up here that's stuck to the x-axis between -1 and 1. This could be the right choice of coordinates for that. I'm not really showing you this so that you can learn it, if that makes sense. There's a time and a place to go and learn more maths if you want to, just to write down what was going on there. That was ellipsoidal coordinates, using a function you've never heard of. Someone, who's in the chat? I don't know what that is, but I'm sighing. Okay, fine. I'm going to call these U and V. These super weird coordinates. The point I'm really making is that there are weird choices out there. These are called ellipsoidal coordinates, and they're my favourite. There are weird choices out there that are maybe the right choice in a different situation. That's sort of the point of what I've been showing you so far. We've seen other examples of this. Let's quickly recap through them. We saw that for squares that are lined up with the axes, you want to just use x and y. It's a good choice of parameters there for describing where those points are. For things that are at a different angle, you might want to choose something like x plus y and x minus y. That might give you a nice answer at the end, rather than lots of different inequalities. For circles, there are these things called polar coordinates, where you write x is equal to r cos theta and y is equal to r sine theta, and you just deal with it. And it turns out that's a great way of describing circles. And for ellipses, you've got choices. You can either stretch your polar coordinates out, or you can define these weird ellipsoidal coordinates that give you other options and other choices about how you describe where points are, depending on what it is you want for a particular problem. There are lots of other choices as well. What are people saying in chat? Harriet can see why they're my favourite. I hope that I'm conveying that they are my favourite. They did a lot of weird stuff. These red lines I haven't talked about that much. So the blue lines are the ellipses. The red lines, and isn't it weird how they all seem to be going through their origin? They all come through this and out the other side. The red lines are hyperbolas, which is something I can't remember when I learned about hyperbolas. Hyperbolas have equations like x squared minus y squared equals 1. I think that's true. Yeah. They've got equations that look like the equation of a circle, but with a minus sign in the middle. I hope that's true. I've got a horrible feeling as I say that I've not put the right number of minus signs in. Yeah. Looks like a slinky, right? Okay, warm. Okay. So let's do an actual application. If you have something like a fluid dynamics problem of a bucket with a hole in the bottom, and the water's going through the hole, by gravity it's falling out of the bucket through the hole in the bottom, then the red lines here describe the flow the flow lines of what you get as a result of how the water in the middle just falls straight down and the water around the sides flows around like this along those red lines in order to get out. That's one solution to fluid dynamics equations. So there's something really weird going on, something like, what's going on? What's the difference between hyperbolas and rectangular hyperbolas? It's probably not the right time. Oh, Harriet's given me an equation for hyperbolas which has a squared in it and b squared in it, which I probably meant to say. I think the rectangular ones are the ones that are lined up with the xy axis, like in Harriet's formula, and there's a class of other ones with oblique asymptotes, but I've used loads of words there, and this live stream's already got far too many words in. So writing down parameters of where points are is helpful if you're trying to describe where stuff is. It's a skill that people find really difficult, especially at university, where we start trying to write down where stuff is so that we can do some integration over it, or find some volumes, or work out what's going on across some surface. Thinking about my fluid dynamics problems, thinking about how much water is coming out of the bucket, how fast is it going. I'm going to need to do some integration perhaps to work those things out. It's really hard because you need to describe where the stuff is before you can start doing crazy integration stuff over that region. I think I'm going to set a problem as homework because I'm running out of time. It's a 3D version, which is to think about which points in terms of x, y and z are inside a cone that has height h, and the base is a circle with radius r. So which points are inside this cone, height h and radius r. Now, you know what a cone is, and hopefully my height h and base radius r is not too surprising. But in terms of x, y and z, actually writing down these inequalities is surprisingly tricky, and then converting them into some system where the things are just between numbers instead of, or things are just between numbers or functions of the other variables. But to try and solve those inequalities, to get them down into a nice form, is surprisingly tricky. So I think I'm going to leave this one as homework, to say, can you try and work out a way to explain which points are inside this cone using inequalities. Writing down points like this is also fun for just describing where stuff is. I've got an amazing book that does this for pasta. I'm going to show it to my webcam. It's going to be a little bit tiny. It's called Pasta by Design, and all of the book is equations to try and describe what shape pasta is for different sorts of pasta. I'm trying to find you a good page. So a classic page has got some pasta in it, and then also some equations to describe that shape of pasta, to explain where the pasta is, for lots of different shapes of pasta all the way through. It's a fantastic book because it's all about pasta, but it's also all about maths. So there we go. I had a look just before I went live. I had a look online, and it's been out of print for a while, so it's almost impossible to get. It's not recommended reading or anything like that. It doesn't even have words in, so I don't know how that would work. There's not a book recommendation. It's just people can use this to describe, I suppose, architectural stuff and where your building is supposed to be, but also things like what shape is pasta? Where's the pasta? Ooh, somebody's put conic sections into Desmos. Fun. Harriet's finding it in German for £60. I cannot recommend that at all. Words cannot express how much I do not encourage you to get a design book about pasta in German for £60. Right, that's I think best recommendation I've given anybody. Yeah, so Molly's identified the reason that I got it as well. It's my two favourite things, pasta and maths, right? I got it when it was in print, not in German, and not for £60, my word. I saw another copy on Amazon for £170. I mean, good luck, yeah, so Alfie's found it too. If you're selling a copy for £170, then, I mean, good luck to you. It's a very strange book. It's hard to think of an actual use for it. Okay, there's the pasta at the end. Did I show you the donuts as well? Yeah, there we go. Alfie's found it for 100. Who's that? It's a used copy as well. Makes me think maybe I should sell my copy. Anyway, it's full of equations and full of pasta. There's some weird books out there. Brilliant. I'm not putting it on the Oxford reading list as a suggestion, but I'm being very clear that I'm not putting it on the Oxford reading list. I have one last extension that I wanted to show people, which is more donuts. I'm doing this for a different reason, but I've used something like this to try and explain where donuts are. This is a bit like the pasta book, but with a donut. This is a plot. It's a 3D plot with lots of points in, where I'm trying to describe which points are on the surface of mathematically a torus, but a donut, I guess. And I've done that by writing down some variables for my computer to loop over, to have some range of values, just for the surface of the torus. That's maybe a little bit tricky using x and y and z variables. So what I did was I wrote down what I thought were the best variables to do this, and then looped it. You can sort of see in the picture maybe the structure that I've used for thinking about what shape the torus is. You get different choices. There are other coordinates that we could use. So I use this to try and draw a torus in my computer software, because the thing I really wanted to draw was this thing I've heard about of you can link two toruses together. I'm trying to work out how to visualize this. I want to make a good visualization of this. If you set the radius of, it's complicated, but if you choose the radiuses of the toruses just right, then you can have this cool system where one loops through the other one and they fit together quite neatly. So I'm trying to get a good setup for that. When I do a Maths Club session on Pasta by Design, a book that I have that apparently you can't buy, well, I guess I maybe would put donuts in it as well to try and explain what this picture is. This is what I was trying to do, to try and get to describing where these points are so that I can draw them. I think this might be handy for animation as well. So there's some animation technique called UV mapping, where you try to describe where your stuff should be as a transformation to say, here are the coordinates to take the texture that I've drawn and to draw it onto the surface or whatever the thing is. It's sort of a transformation, like how the rectangle for r and theta got transformed into those curved Pac-Man regions. There's some technique, I think, I'm not an animator, some technique called UV mapping that does something pretty similar. Cool. Maybe pasta at some point, maybe donuts. Cool, okay. That was, I think, as predicted, one of the weirder Maths Club sessions. Going over several different things that I'm interested in. I think you can't buy it. Money can't buy this book. I think I'm going to wrap up there, just really quickly, because I can. If anybody wants to ask any questions or chat, I'm going to stay live for a little bit. But if you're heading off, then nice to see you. But if anybody asks a question now, then I will answer it live, because I can. I'm still here. What's my... Oh, I've got a notification here. No, that's fine. Cool. Complete mess, but fun. Yeah, okay, thanks. That's a review. Having a guest with something planned is more structured, yes. Thank you, Andrew Wiles. Thanks for coming along. Thanks for letting us name the building after you. If you're coming to the open days, you can come to the Andrew Wiles building to see that. Local Amazon, £20. Oh, it gets me equations about maths. People are saying thanks. Thanks for coming along. Thanks, Molly. Thank you, Faith. Thank you, who has also called me Jim. You want the Desmos thing? I would put the Desmos code in chat, but let's talk about Desmos. What's this doing? So this has got this one, right? People are coming to it all adds up. Let's see you next week. Let's turn this down. So what it's really doing is it's got some functions built in. I've called them functions of u and v, which is maybe a bit confusing, which is loaded up so that I can put whatever I like in here for my functions. So I can do something really weird like this. And these bits are to show a grid. The grid's got some pretty complicated equations P1, P2, Q1, Q2 that are not that important. It's just to trick Desmos into drawing a grid. And then I've got the functions applied to those grids. So this is F, open bracket, the grid nonsense, P1, P2, and G, open brackets, grid nonsense again. Sort of a function of those particular values of r and theta, or whatever the input variables are called, along the different lines of the grid. This is a nice kind of flower shape. I've got some parameters for the edges of the grid, and here are the hideous functions for tricking Desmos into drawing a grid. I got these from, there's a very good Desmos thing out there for a 3D function, a 3D graphing function thing. If you search for Desmos 3D, it's the top hit, and it's really good. I have shamelessly copied the code for tricking Desmos into doing a grid from that one. Cool. Oh, does Desmos know about lists? Desmos knows about lists, right? Desmos chat. Amelia's learned about polar coordinates. Can you imagine how I would have structured this session differently if I'd realised that I was teaching people about polar coordinates? It might have been less fun, right? Might have done less stuff, might have done more polar coordinates. Thanks for hanging out and learning about polar coordinates with us. I hope you learn them properly in an A-level maths class or something equivalent. They're not hard. I've made them look hard, but that's just me. Okay, cool. Okay, I need to learn about lists in Desmos. This is always good because I'm always aware that on average chat is much better at Desmos than me, so I'm doing this weird hacky stuff that I've copied off someone else, but maybe I could be copying off Desmos instead. Is this 3D Desmos thing? I'm going to put it on the stream just because I can. Hang on, let's go and grab this. So if I search for something like 3D graph Desmos, which is quite, I imagine, quite a common search, because people would love it if Desmos could do 3D, then the top hit I get is somebody's made this. They've got a logo down here. They've worked out how to put their logo into Desmos. I've got this, which is amazing. You can rotate it and everything. It's just brilliant. I stole the idea of how to make a grid off this. I cut out all of the 3D stuff. But if I want to do 3D stuff, I'm going to definitely come back here and use this code as well. Who made this? How do I find out who made this? I would like to cite you. I cannot see a name or anything. I've got an MD globe logo. Well done, whoever made this. It's really good. Cool, right, good. Okay, we're going to end the stream there. Thank you very much for watching along. What maths events are there for Year 12s this year? We're doing some open days. We're doing some open days. If you search for University of Oxford Maths Open Days, they're coming up. We're doing some more in the summer. And we're doing things like this, including a math live stream launching in August. So keep an eye out on the maths website and in general around on the Oxford website and things like that. Follow us on social media. We're doing a bunch of other things as well. Cool. What's that quantum physics? I know, it's just the best Desmos plot, right? It's got not this, the 3D one thing. Isn't it amazing? Right, cool. Okay, I'm going to wrap up there. That was a fun extra 10 minutes. But I think it's time to call it a day. Have a nice evening, everyone. Hopefully a more structured plan for next week. I'll see you next week for another episode of the Oxford Online Maths Club. I've been James. Bye.